Welcome to this explainer. We are jumping right in today because we have a fascinating topic. We are going to decode the absolute mystery of motion. We're talking about kinematics. Whether it's the science of going straight or spinning around, we're going to cover how humanity went from ancient, totally incorrect guesses to razor-sharp, modern problem solving. So let's just get straight into it.
Here's our roadmap for this explainer. We'll start with the history of motion, move on to the language of physics, look at the equations for going straight, get gravity and free fall explained, and finally, do some real problem solving in physics. We're building this block by block so you can tackle these concepts with total confidence.
All right, Section 1, the history of motion.
You know, for physics students today, it's kind of wild to think about how incredibly wrong we used to be about the world around us. There was this massive 2,000-year gap where Aristotle's ideas just completely dominated Western science. It wasn't until the 1500s and 1600s that Galileo and later Isaac Newton totally revolutionized the science of mechanics and gave us the true foundations of motion.
Aristotle's reasoning is actually pretty fascinating. He basically believed everything was made of earth, water, air, and fire. So, in his mind, a stone falls simply because its natural place is on the ground, and smoke rises because its natural place is up in the air. Essentially, matter just wants to go home. Now, that feels super intuitive to our everyday experience, right? But scientifically, it's completely wrong.
Enter Galileo in the 1500s. By rolling balls down inclined planes in really careful experiments, he introduced an absolutely vital concept: inertia. He proved that objects don't magically seek out some natural place. Instead, a moving object, like a hockey puck sliding on perfectly smooth ice, will just glide on forever in a straight line, unless something like friction forces it to stop.
Moving right along to Section 2, the language of physics.
If we want to really understand Isaac Newton's math, we first have to learn the specific vocabulary used to describe an object going straight. We divide our measurements into two camps. Scalars only have a size or a magnitude. Think of speed, mass, or time. Vectors, on the other hand, have a magnitude and a direction. So speed is just how fast you're going, say 60 miles per hour. But velocity is a vector. It's 60 miles per hour due north.
And that brings us right to velocity, the rate at which position changes. Because it is a vector with a specific direction, we can use simple math symbols to tell us exactly where it's going. A negative sign in front of a velocity value doesn't mean you're going slower than zero. There's literally no such thing. It simply means you're moving in the opposite direction.
Okay, Section 3, equations for going straight.
We're going to take those foundational words and turn them into the 1D kinematic equations that literally govern our universe. Now, don't let the algebra intimidate you. Let's just translate this velocity formula into plain English. It simply says, your final speed, that's v, is just your starting speed, v0, plus however much you speed up or slow down over a given amount of time. That's just acceleration times time. It's beautifully simple logic.
When an object accelerates at a constant rate, the relationship between velocity and time is perfectly linear. As time ticks forward on the horizontal axis, the velocity climbs steadily on the vertical axis, giving us a straight line. And the slope of that line, that is exactly your acceleration.
Now, calculating your exact position, or displacement, is slightly more complex. This equation connects where you are, your starting speed, how fast you're accelerating, and time. Notice that t is squared here. This tells us the relationship between position and time isn't linear anymore. It's quadratic. Let's see how that looks visually. Because of that quadratic equation, the graph of your position versus time isn't a straight line, it's a parabola. The curve shows the object covering greater and greater distances with each passing second as it speeds up. It literally sweeps upward exponentially.
Section 4, gravity and free fall. We're going to take these equations and apply them to the most relatable example of constant acceleration we have, the invisible force holding us down to Earth. Let's get gravity explained by testing your everyday intuition against the laws of physics. Do heavy objects fall faster than light ones? If I drop a bowling ball and a feather from the same height, which one hits the ground first? Well, here is the counterintuitive truth. We are so used to air resistance slowing down feathers that we automatically assume mass dictates the speed of a fall. But imagine an astronaut standing on the moon where there's zero air resistance. If you drop a feather and a heavy metal shot-put ball there, they hit the ground at the exact same time. Gravity is entirely independent of mass.
This gives us the golden rule of freefall. Close to the Earth's surface, the acceleration due to gravity gets its own special symbol, a lowercase g. It's a constant downward acceleration of 9.80 meters per second squared. Everything, you, me, a falling rock, accelerates downward at 9.8 meters per second every single second.
And finally, Section 5, Problem Solving in Physics. Let's take every single concept we've covered and do some actual problem solving together. Paint this mental picture with me. Someone stands on a cliff and tosses a rock straight up. Our starting velocity is a positive 13.0 meters per second. At the exact same time, gravity is pulling down at a negative 9.8 meters per second squared. We want to find out exactly where that rock is after precisely 1 second.
Here is the secret to mastering physics. It's just a logical puzzle. Step 1. Identify your knowns. We have velocity, acceleration, and time. Step 2. Pick the equation with only one missing piece. In this case, our displacement formula. Step 3. Plug those numbers in and let the math do the work. The result? The rock is 8.10 meters above our hands. Let's analyze the rest of the rock's journey using that exact same math. At 1 second, we know it's 8.10 meters high. But by 2 seconds, it is dropped back down to 6.40 meters. And at 3 seconds? The position is negative 5.10 meters. That negative sign simply tells us the rock has fallen past the edge of the cliff and is now below our starting line.
When you stack the graphs of position, velocity, and acceleration, you see the perfect symmetry of physics. The position curve shows the rock going up and falling down. The velocity line steadily drops from positive to negative. But notice the acceleration line at the bottom. It is perfectly flat at negative 9.80 the entire time. Even when the rock completely stops at its absolute peak for a fraction of a second, gravity is still pulling on it just as hard.
So the crucial takeaway here is that free fall doesn't just mean falling down. Free fall applies to upward motion just as much as downward motion. Gravity is a relentless, constant background rule of our universe. It dictates the ascent just as fiercely as the descent. It literally never turns off.
We've seen that gravity is a constant acceleration, acting equally on a feather, a metal ball, and a tossed rock. If the math is this beautifully predictable, what does that reveal about the invisible scaffolding holding our entire universe together? It's mathematically perfect, and it's just waiting for us to understand it. Thank you so much for joining me on this explainer. I hope you leave today eager to explore these incredible laws of physics even further.